Okay, so looking at pendulum problems. First one, what is simple harmonic motion? So for something to be in simple harmonic motion, it means that you have to have a mass that is moving and oscillating. It needs to have an equilibrium point in the middle, and there needs to be a force that is making it return to that equilibrium point, some restorative force. Okay, so pendulum, spring oscillator, guitar string, anything that follows like a sinusoidal sort of motion. Okay, a simple pendulum swings with simple harmonic motion. The mass of the pendulum is 3 kilograms, and the length of the pendulum is 1.5 meters. The amplitude of the swing is 0.2 meters. All right, so looking at our known data, we've got mass of 3 kilograms, we've got length of 1.5 meters, and we've got amplitude of 0.2 meters. Okay, we're looking for the period of the swing. So when you're looking at the period of a pendulum, at least for a simple pendulum for relatively small angles, the period is going to be equal to 2 pi times the square root of your length over gravity. Okay, so in this case, we've got 2 pi times the square root of 1.5 divided by 9.8, because it didn't mention anything about like being on a different planet or anything. All right, so we've got a period of oscillation of 2.46 seconds. Great. Now, the maximum speed of the pendulum bob and the state where maximum speed occurs. Okay, so when you're looking at simple harmonic motion, your maximum speed is just going to be 2 pi times your amplitude divided by your time. Okay, so looking at our amplitude and our time, that's just going to be 2 pi times our amplitude of 0.2, and then dividing by our period, which was the 2.54. There we go. So that means that we have a max speed of 0.511 meters per second. Half a meter per second. All right, now looking for the maximum acceleration. Okay, that formula is looking at, for our maximum acceleration, that's going to be 4 pi squared times our amplitude divided by our period squared. Okay, so plug in those numbers in. 4 pi, our amplitude, 0.2. Sorry, I forgot a squared in there. 4 pi squared times our amplitude of 0.2 divided by t squared, which is 2.46 squared. There we go. So our maximum acceleration, we've got 1.30 meters per second squared. There we go. Chugging on through. D, the maximum net restoring force. All right, so we don't have a specific new formula for finding that force, all right, but we do know what our max acceleration is, and we do know what the mass of this thing is, which means that we can go back to our old friend Newton's second law and use F equals ma. All right, so we're just going to be doing our acceleration times 3, and that gives us a max force of 3.91 newtons. Cool. E, calculate the following when the pendulum bob is 0.12 meters from the equilibrium position, lowest point of the swing. All right, so we are, if we're looking at this thing swinging around, right, we've got a total amplitude of 0.2. We're a little bit inside of that. Okay, so we're not all the way out there, which means that we're not looking at one of the ends of its motion. Okay, we're looking at some intermediate point, so using our intermediate velocity and intermediate acceleration formulas. Okay, so the speed of the bob for EI, that's just going to be our speed in simple harmonic motion, our intermediate speed, which is equal to our max speed times the cosine of the inverse sine of our displacement over our amplitude. Okay, so our displacement over amplitude, we're looking at 0.12 meters. Okay, so 0.12 divided by our amplitude, which was 0.2. So 0.12 divided by 0.2, that gives us 0.6 in there. The inverse sine of that is 37-ish degrees. Cosine of that, 0.8. And then we're just multiplying that by our max speed, which was times 0.511. 0.511. There we go. Which gives us a intermediate speed of 0.409 meters per second. Okay, and we should expect a slower speed here because it's not at its maximum speed. Okay, the pendulum bob, looking for its acceleration now. Acceleration formula very similar to the max acceleration. The only difference is instead of having our amplitude, we're just going to have whatever our displacement is right there. Right, so 4 pi squared times x over t squared. Okay, so plugging in our numbers, we've got 4 pi squared times our x, which was the 0.12 meters, divided by our period squared, so divided by 2.46 squared. Okay, and that ends up giving us an acceleration of 0.783 meters per second squared. All right, so again, not at our max acceleration, so we should expect a smaller acceleration on this than we did for our max. Okay, and then the net force on the bob, again, we could just use F equals ma. Okay, so multiplying this 0.783 times 3. And that ends up giving us a force of 2.35 newtons. Cool. So now we're done with that. The frequency of oscillation, all right, that one's going to be a real quick calculation because frequency is just the inverse of our period of oscillation. Okay, so we got a period of oscillation of 2.46, taking the inverse, bang, we got 0.407 hertz. Remembering our units for frequency are hertz, or you could also do seconds to the -1. Same deal. Okay? Look at that. We're done with number 2. Let's look at the next one. Number 3. You wish to build a simple pendulum which will swing with a period of 1 second. Describe a simple pendulum. So a simple pendulum is just a pendulum bob hanging on a string that is hanging from a pendulum holder, and it is swinging along a single axis. All right? You don't want to let it swing off in different axes because then you're looking at more complicated sort of motion. You don't want to have like a double pendulum where it's like going down to one bob and then another bob hanging off it. That's like completely random motion. All right, we want just single bob going back and forth. Okay, boom. Explain how each of the following will affect the period of the pendulum. So length of the pendulum. If you're looking at the formula that we have for the period of the pendulum, we got this 2 pi root L over G. Okay, so if you increase the length, right, it's in the top of that numerator, which means that it's going to be increasing the period. Now, it's not going to be doing it directly because you've got that square root, all right? Basically, the square of the period is directly proportional to L, right? Because getting the square root off of there, getting L and T on equal terms, you're going to have to square that over there. So you end up with T squared is proportional to your length, okay? The mass of the pendulum, mass isn't in there, so mass does not have an effect. Gravitational acceleration, that's in the denominator here, so the larger that gravity gets, the smaller your period will get, all right? But again, it's not a inverse relationship because you've got that square root in there, all right? So the period squared is inversely proportional to gravity, right? Again, moving that square root off just so you don't have that to the 1/2 power on there, okay? Next, the amplitude of the swing. You don't have amplitude in there either, all right? So no effect from mass, no effect from amplitude. And as length gets bigger, period gets longer. As the gravitational acceleration gets bigger, period gets smaller, all right? C, assuming you're on Earth, calculate the length of the pendulum. Okay, so we're using this formula here. All right, we're assuming we're on Earth, so we've got a gravitational acceleration of 9.8, because we're assuming we're on the surface of Earth. We've got a period of 1 second. We're just solving for L. All right, so moving this thing around, that's going to be T over 2 pi. Getting that square root off of there means we're squaring it. And then we're looking for L, so multiplying G over. Okay, so our period is 1 divided by 2 pi. So 1 over 2 pi. Squaring that, multiplying by 9.8, gives us a length of this pendulum of 0.248 meters. Done. That was easy. Next one, number 4. A rope is attached to a bowling ball so that when the rope is tied to the ceiling, the bowling ball and rope will swing as a simple pendulum. The bowling ball has a diameter of 25 centimeters and weighs 72 newtons. The weight of the rope is negligible. The bowling ball is displaced at an angle of 15 degrees from its equilibrium position and released. Using a stopwatch, you measure the period of oscillation to be 6.4 seconds. Describe how you measure the period of oscillation, that is, when do you start the timer and when do you stop it. So if you're looking at one full period, it needs to swing all the way through the oscillation. So like from one end all the way to the other, all the way back. Okay, so probably if you're timing this, shut up. Yep. Any second now. Cool. So when we're looking at the oscillation, you probably want to let it swing more than one time, then just divide by how many times you let it swing. Use the period of oscillation to determine the length of the rope. Okay, so it tells us that we've got a period of oscillation of 6.4. So looking back at this formula here, again, assuming that we're on Earth. Okay, so 6.4 divided by 2 pi, squaring it, multiplying by 9.8. So that gets us a period of oscillation, sorry, a length, my bad. So 4A, no, not 4A, 4B, there we go, a time of 1.2 seconds. Okay, so we've got a period of oscillation. Now we're looking for the speed of the bowling ball as it passes through the lowest point of the swing. All right, so at its lowest point, that's where it's going to be going the fastest. So effectively what we're finding here is the max speed of this thing. Okay, so max speed whenever something's in simple harmonic motion, remember, is 2 pi times our amplitude over t. Right, we've got t, we've got pi. We do need to know what our amplitude is, so let's look at this thing real quick. It tells us that we've got this pendulum off at an angle of 15 degrees. Okay, the amplitude is this side of this triangle. We have the length of this period, the length of this rope. Right, we got. Did we find that? Wait. Oh, I'm dumb. The period was 6.4. This is the length. So we have a length of 10.2. There we go. So we've got a hypotenuse, we've got an angle. We're looking for this opposite side, which means that we're going to be using sine. Okay, so sine of our angle, so sine of 15 equals opposite over hypotenuse. We're looking for the opposite side, so I'm just going to multiply that hypotenuse over. So 10.2 times the sine of 15 equals that amplitude. Okay, so 10.25 times the sine of 15. There we go. So we've got an amplitude of 2.65 meters. All right, so plugging stuff in. We got 2 pi times 2.6. How did K get in there? 2 pi times our answer divided by our period of 6.4 seconds. So that ends up giving us a speed, a max speed of 2.6 meters per second. Great. D, determine the tension on the rope as the bowling ball passes through the lowest point of the swing. Okay, so when we're at the lowest point, that's where you have the smallest acceleration, right? Side to side, this thing isn't applying any forces, which means that it's just going to be canceling out any downward forces. In this case, the downward force that we've got is the weight of the bowling ball. So that's going to be 72. All right, so canceling that out, it has to be 72 newtons as well. There we go. We got our tension on the rope. A 60 kilogram person sits on the bowling ball. The bowling ball is again displaced 15 degrees from its equilibrium and released. What will be the period of oscillation? So all we've changed is the mass. Mass does not have an effect on the period of oscillation of a pendulum. Okay, so what that means is that our period will be the same. Okay, so for E, still going to be 6.4. Okay, F. The following changes are made. The person sitting on the bowling ball is replaced with another person whose mass is 40 kilograms. Will not make a difference. The initial displacement of the pendulum is changed to 5 degrees. Amplitude doesn't make a difference. And the length of the rope is reduced to 1/2 of its original length. That will make a difference. And the whole apparatus is moved to the surface of Mars where the gravitational acceleration is 3.98 meters per second squared. That will also have an effect. Okay, so determine the new period of oscillation. All right, so now looking for our period of oscillation, we got this T equals 2 pi root L over G. Okay, we've got new L's and G's. Okay, so we've got the square root of L. Our original length was 10.2. Okay, so that's just going to be 5.1 as our new length because we had half the original length. And then gravity going to be 9.8. So that's our root L over G. We're just going to multiply that by 2 pi. Boom. We've got a period of oscillation of 4.53 seconds. Okay, so a smaller period of oscillation because we had less length. We did have less gravity as well, which should have raised our period, but it looks like the length change was larger. Okay, so there we go. There we go. We got a period. And we're all done. Hooray! It's all done. Yay! See you guys later. Bye.